Good morning and welcome to this lecture by Dr. Thomas Thundat, our distinguished alumnus. He's a 1980 M.Sc. Physics from IIT Madras. He's currently the Professor and Canada Excellence Research Chair at the University of Alberta in Edmonton. Prior to that, he was with UT Bethel, Oak Ridge National Lab as a corporate fellow and leader of the Nanoscale Science and Devices Group at Oak Ridge National Lab. He is also a research professor at UT Knoxville, visiting professor at University of Burgundy, France, distinguished professor at IIT Madras, and centenary professor at IISc Bangalore. He received his PhD in physics from SUNY Albany in 1987. He has more than 335 publications in refereed journals, 45 book chapters, 40 patents. He is the recipient of many awards. He is also an elected fellow of the American Physical Society and Electrochemical Society, American Association for Advancement of Science, and American Society of Mechanical Engineers, and SPIE. His research is currently focused on novel physical, chemical, and biological detection using micro and nano mechanical sensors. Although I understand his lecture today is on a completely different topic, off the beaten track, so we are all very excited to hear about what he's going to speak on. I also want to thank Professor Thundat for participating in the Institute review that just happened from Monday to Wednesday, and I'm sure the findings and recommendations of the committee will help us greatly as we move forward. So with that, I invite Professor Thundat to deliver his lecture.
Thank you very much for this opportunity. This is a crazy topic. I never given this talk before. So, and generally I don't have courage to give this type of talks to other people, but IIT Madras is like a home. So between home, we can say all kinds of stuff. So you have to be a little patient with this thing. So the title of the talk is Reviving Nikola Tesla, and I'm not an electrical engineer, I'm a physicist. Now I'm in chemical engineering though. So this is my group, there are lots of people. We moved from Oak Ridge National Lab to Edmonton. So this is the preamble. Basically, before we go into this crazy talk, imagination is more important than knowledge. So, and this is from Feynman. If you can imagine it, we can make it. So remember this. So this is Nikola Tesla. He came to US to work with Edison in, I forgot what year. And they, of course, they had lots of fights after, Edison was Edisonian approach, and then Tesla was a little different. I will give you some of the examples. And here this is one quote from Tesla. If you want to find out the secrets of the universe, think in terms of energy, frequency, and vibration. So he said this a long time ago. At that time, even the existence of atoms and things like that, we were not sure at that time. And then, of course, Tesla and Edison got into this fight, AC versus DC, and of course, the Edison tried to make Tesla looks like a crazy guy. So this is what Tesla had to say about Edison. If Edison had this basically Edisonian approach, you try until it works. That's Edison's approach. So we call this. We try to discourage students from using this type of idea, saying that okay, think always, stop working, start thinking. That's the idea here. So Tesla had lots of different ideas. One of them was free electricity to whole world. So he made up this tower, this huge tower. It had a big dome at the top. And the idea was to give power to all the people in the world. Unfortunately, J.P. Morgan, who funded this idea, Morgan is a is a businessman. And Morgan asked Tesla, so how can I charge people? People are getting electricity. And Tesla didn't have an answer. So Morgan said, forget it, I am a businessman. I need money back, return on investment. So Tesla, of course, got discouraged, and he died as a poor man in New York City hotel a couple of years later. So this is one of the things, and he wanted to use electricity from the air. We know that now there's lots of charge exist in atmosphere. Actually, a huge amount of electricity, which we haven't still tapped yet. So one of the what I'm going to talk about is that wireless power. So this is starts with 1826 ampere, trying to the magnetic field, and you can produce electricity. Of course, Faraday came along, Maxwell, and we have J.C. Bose here, and he also showed some interesting things. Of course, Marconi, and then of course Tesla, and actually Marconi's idea on radio is actually Tesla's patent. So Tesla actually won a couple of maybe after he died, it went into court, and then the court said actually Tesla originally invented the radio, not Marconi. Then comes around 2007, MIT guys demonstrate 60 watt power transmission 2 meters apart, and these are the people. So John Paulus is right here. So here a copper wire made it in a loop, another loop, and you can see the light bulb comes on. These guys are standing in between this magnetic field. So this creates a magnetic field along the axis, and of course it's a AC, around 9.9 megahertz. It produces around 45% efficiency. The light bulb comes on, and this wire is like a size of my finger practically. So you can also do Tesla coils. This is one Tesla coil we made at the lab, and it can create a power, very high electric field, 10 to the power 5 to 10 to the power 6 volt per meter around the coil. So if you walk around with a let's say with a fluorescent lamp like these tube lights here, it will light up. And this is a common show. People do it at high schools and things like that. You can walk around and this will be working fine because electric field actually exists in the air atmosphere. It basically accelerates the electrons and then they collide and they produce the light. Or you can actually have power. I'm standing at a 1 potential and he's at a 1 potential. Electricity is going through me to him. One of us is in a higher potential than other guy, and you can actually this is an incandescent light bulb, and it works fine. So we thought we will do an experiment with the Minister for Science. This is a Canadian Minister for Science. He came from Ottawa to visit us, and I said, okay, why don't you see this? So he's holding a light bulb, and my student is holding another part, and it comes on. So actually you can have electricity from the electric field. You can create the huge electric field in this room, and you can power everything. But there is a problem. I called the vice president for research and said, why don't you come to my lab and I will show you some great stuff. So he came around with a visitor from Qatar, some big guy from Qatar, and they were playing around with the light bulbs and tube lights and things like that. And the Qatari guy liked it so much, he took his cell phone and gave it to the vice president, our vice president, said, please take my picture, holding this light bulb. And unfortunately, the vice president was on 1 potential, and the Qatari guy was another potential. They had a potential difference, and of course, the vice president got a shock. So that is the end of it. So we thought, okay, forget this, we need to move on, because it works with all cell phones, but the cell phone from the guy from Qatar was somehow different. I don't know. We still don't know what happened. So we stopped that and we said, let's see, we think of something else, right? So the question we ask is that, do you need to have like a two wires for electricity. Like, there are two holes, you can plug your stuff in. That's the way it works, right? And from the childhood onwards, we have been told that it comes through here and it goes through the other side, and it comes up like this, So we wanted to test it out. So this is the idea. So you have the source somewhere in some generator. It produces electrons by Lorentz force. Push the electrons move back and forth with producing electromotive force, and that creates the power basically. So we thought of a different idea. Maybe we don't need two wires. We need only one wire. It's kind of interesting in the sense that you have to get away from your comfort zone, because we always think in terms of two wires. Can we do with one wire? There are lots of applications. So I have to show you this movie. Hopefully it works. This is my postdoc. It's an aluminum foil, and this is the wire that is coming in, single wire. It's a wooden stuff. This is a 50-watt light bulb. There you go, it works, right? So there's only one wire and the electrons have no place to go. Just a single wire connected to aluminum foil, and he can touch it, and he's still around, so he's not dead. 50 watt, it can be a little too much. So what we are doing, we are taking a wire and we converted this into AC, 3 megahertz, actually 6, and produce a standing wave. So this is a quarter wave resonator, standing wave, and between this point and this point there exists a potential difference, AC potential difference. So if you connect between this light bulb, it should light up. That's the idea. It's very naive, but it kind of works, So just let's go by the naive ideas at potential difference here to here. There is a difference and you can use it. So we didn't know what to do with this wire. This is maybe 5 meters or something. So we put it into a coil. It doesn't have to be a coil. It can be long, or it can be rolled it into a ball or something like that. No magnetic field. That's what I'm trying to say. So it's connected between 2 points on the wire itself, basically shorting itself, and it works. So this is a metal desk we found in the lab. This is a linoleum floor, it's completely insulated. Again, you have this wire coming in, connected to the table, and let's see whether you can power something up. Again, my postdoc Charles. There you go, it's working fine, right? It's a large area. You can put it anywhere you want, and he can touch it, he can sit on it, nothing happens. Of course, there is a insulating plastic or something on it too. So it even go through the plastic and still you can see it. So, but it cannot go too far. It gets to be very thin plastic, maybe a couple of millimeters or less than a centimeter. So we made up a Christmas tree lights. This is a interesting stuff. We found the light. You can buy it from Walmart. You just cut the one end, and so you have no return path, and all the lights comes on. And so, of course, there is a big market for this thing, what you call the cell phone charger. And again, there is a movie here. There you go, it starts charging. Again, remember, this is only one wire, and this copper sheets, basically, we made it into stripes to avoid what you call the eddy currents. You don't have to do it, but we thought it's better to have it like that. So we get something like a 95 to 97% efficiency, and so this is pretty good actually, very high efficiency. The MIT guys had 50% or so, 45% efficiency, but we have around 97% efficiency. So think about the possibilities. You can actually convert this whole room into a wireless power. You can have some kind of a conducting thing underneath the carpet, and you can have, like in the old days, people used to have what do you call, oil lamps. You can have the light bulbs wherever you want, you can carry it around and it works, you know. So we can go back in time, but not oil lamps, but light bulbs, you know, and very efficient. So we are no more slaves to these outlets and things like that. So when you guys design buildings, of course you have to figure out where the power will go, and you know, all these things. Is no more. We don't need that anymore. So it started with a different story. Actually, I kind of told you a roundabout way. Actually, we were working on sensors. We worked in sensors for a long time at Oak Ridge National Lab, and finally came up with a little device. This is a MEMS sensor sitting underneath this titanium frit, and all the electronics, all digital electronics actually, you know. Then it also has a telemetry for 8-channel wireless, and it works with 2 hearing aid batteries, and we implanted this in a rat to look for the blood gases. The reason is that in the US, there are lots of drunk drivers sitting in the jail. They are very nice people, you know, you cannot find a better person than a drunk guy, but nice guys, but when they drink, they have problem, they cause accidents, so government decided to put them in the jail. But if you can release them on a voluntary basis or something, they can be productive citizens contributing to the economy, right? Instead of putting somebody in the jail, that's a bad idea. So they started doing with a watch called, you know, alcohol watch or something. You put them on the person, send them home, and these guys are so addicted, like Lindsay Lohan, you know, she's always in and out of the jail, right? So they take this watch and put it on their wives, you know, and so this watch is actually reading wife's alcohol level, not their person's, and the guy drinks, go to bar and drink. So they kind of figured it out. Maybe it's not a good idea, you know. Maybe we want to have something more, better than that. Maybe we can implant them in the people subcutaneously, under the skin. So the body fluids come around and equilibrate through this frit, and you can actually look for the blood alcohol level, and actually cocaine too, because there are lots of addicts, cocaine and all kinds of stuff. In addition, it also has applications of biomedicine. You want to look at the carbon dioxide, oxygen, and all kinds of other things like acetone, methane, and so on, because all indicative of diseases and so on. But the problem is that we implanted this in the rat many times in the Indiana University. We were working with a doctor there, and the problem is that the battery lasts only for maybe 2 weeks, you know, and then it doesn't work. I mean, then you have to cut open the rat again and change it again, and so this is a not a good idea to have tiny little batteries like hearing aid batteries. Like for example, pacemakers. Pacemakers is maybe this big, right now. 10 years ago, this used to be much bigger. Now it is much smaller, but the whole thing is a battery and a little electrode. So if we can remove the battery, suddenly it opens up all kinds of stuff. I can have all kinds of stents in my head and all over the body, reporting all kinds of things wirelessly without any batteries. So it opens up an enormous amount of possibilities. So we decided to do an experiment on Charles, you know, is my research associate. So he's actually wearing it on his leg in a power source connected to his leg, and there is a light bulb coming out, a sensor coming up on his connected to his skin. It could as well be inside his body, you know, basically saying that the body works like a single wire, and the sensor can be inside, detecting all kinds of things, you know. So you don't need batteries inside, you can have it outside. So if it goes wrong or something, you can change it, right? So this is again coming back to Tesla. You know, what do you do with Tesla now? This is all somehow connected to Tesla. So we can actually have a transmitter like a Tesla coil. Of course, its current and voltages are out of phase, and then you can have a receiver somewhere far away, and then try to transmit electricity from one location to another location. So this is the way. So this is a reactive power because current and voltages are out of phase in a the active circuit. Of course, the electrons are moving back and forth. A light will come up. In a reactive part of the thing, suppose if you have a inductor or a capacitor or something like that, it wouldn't really work because it's a reactive power. It doesn't really, reactive power. Actually, electrical engineers don't like reactive power. They're trying to avoid it. But you actually need a little bit of reactive power for things to work locally. So this is the way you can write a equation. These are simple. This is a voltage, instantaneous power, instantaneous current. You create a phase difference between these guys. So you can do a little bit of algebra or trigonometry and basically come up with, actually you get a 2 cos omega term here. So if you take an average power, so you have to integrate of course over 0 to 2 pi or 0 to t per cycle, then you get 2 terms, and this term is the real power and this is the reactive power, and that's the way people define this. V0 I0 divided by 2 times sine theta, the phase angle between these things. But generally the P average of course is V0 I0 cos part of that thing, and reactive power can be for a little cycle because this will be what you call if you integrate it over a 0 to 2 pi, this term will be 0. So you can actually have 0 reactive power at certain time depending upon the phase angle. So what the heck is this reactive power? Because we don't teach this in physics. It's all electrical engineering, right? So we had to go and talk to electrical engineers and try to understand what is the term reactive power and why they hate reactive power. Because we are all dealing with the reactive power. We are not dealing with the active power because our phase difference is 90 degrees between our current and voltage. So in the circuit, it's basically a LCR circuit, the one I showed you. The long wire, it has a distributed inductance and resistance, and the return path. Of course, there is a return path. It's not a simple wire going nowhere, right? That's what I showed, but that's just a cartoon. But it is a diffused capacitance around, a self-capacitance around it, actually completing the circuit. And that's the way it works. So you can actually write down these terms. Of course, it's similar things from mechanics where L is replaced by mass. Same equations for resonance. And the resonance happens when omega L and 1 over omega C are equal. So you can, at the resonance, you can equate it. So this part is the loss term I squared R, which we call the IR loss. And this is the stored term, basically VAR in electrical engineering. And so the Q factor is P stored by P lost. And so the whole idea is to have a very high Q factor. So this can also work as a storage device if you have a very high Q. So now you see the difference. This is not a what do you call where you are not losing power. Just generally, this device is whatever you have here. Power is created somewhere far away from here, and the minute it produced, you have to use it instantaneously. Otherwise, it's lost. In our case, we are not. We are keeping it in resonance. So you can have a source in Canada, and you can have a receiver here, and the power will be taken only if it is resonantly coupled and the power is used. Otherwise, power will stay in the system like a spring mass system. Exactly same equation, right? So we are expert in mechanics. My whole 20 years, 25 years, I worked on mechanical systems, and this is the same thing, not very much different. So this is what is happening. So if the power is created, it have a self capacitance, and that's the way connected back, it connects the circuit automatically. So this is not a magic. It's okay to think like a magic, but it's not magic. It is this capacitance around it actually complete the circuit. So we decided to make a big tower, just like a Tesla, not that big. Of course, you can see that my postdocs are climbing up on this thing. So we put it on a little cart, so you can pull it around all over the place you want. So this is in a field, so there is one tower here, and another tower here. This is to avoid the sparking, so you can have you can pump lots of energy without creating sparks. And we inject the power into the ground, and it comes out here, right? So this is the way it works. So this is the earth, and this is the first tower, and this is the second tower. And we started doing experiments. So right now it is 100 meters apart, and we can inject a small amount of power at this time. So the reason we are injecting only small amount of power, and we want to make sure that it is safe, because otherwise there will be lots of NGOs or whoever making lots of noise saying that we're going to kill all the people or whatever. So we wanted to go step by step, start with the simple small voltages, and then make sure that nothing happens in the environment or the bugs or flies or whatever is around, they are safe. Safety comes first. So let's talk about application. So the reason they asked me to come to Canada is that to work on oil sands. I don't know anything about oil sands. I don't even know what chemical engineering is, right? So they put me in the chemical engineering department and said, work on oil sands. And I said, when the president called me up at home, I said, I have no idea what you're talking about. I never heard of oil sand. I don't even know where Canada is. I know somewhere up in the north. That's it. And she told me that whatever you're doing is chemical engineering. I said, okay, in that case I will come. So this is Alberta. This is a part of Canada. This is Montana. And there are lots of oil here, actually. But it's in the form of sand. It's like dig out the dirt, and then it looks like that. But from there, you have to convert it into gasoline that you can put it in your car. So first you have to remove the sand, make into this tar, bitumen basically, and then upgrade it into something like that. So Canada has 2.1 trillion barrels of this thing sitting underground. That is trillions of dollars. That's why they are interested in this idea. And of course, it's not the best solution because, okay. So we start with big devices like this one, go around digging up things, and then of course, break them into pieces, put lots of water, hot water and some surfactants, and then transport it through some pipeline, and then get into big towers, and then get rid of this sand particles that goes down. And it's a flotation technique that we learned a long time ago. So let's see. And you have to upgrade it, and then it will end up like a nice clean liquid. And one problem with this, there are actually two problems. First is that the tailings. So for every barrel of bitumen produced, you have 17 barrels of water used, and of which 2.4 barrels of fresh water is lost forever, because lots of tailing, lots of sand particles, especially nanoparticles of clay get into it, and they form a big tailing like a lake, and it's huge. You can see that these are not small, it's huge. This is a Google map, and all these are tailings, and of course Canada wants to get rid of these things. So that's one of the things they asked me, come up with some idea that we can get rid of this thing. So bitumen another problem with the bitumen is that bitumen has lots of sand and clay and a little bit of water on it. So it's a solid liquid interface. Solid will be clay and sand, liquid will be bitumen and water, and then so whatever you produce as the product it has fine particle in it, which are around 100 nanometer wide and maybe 2-3 nanometer thin, and lots of this sand particle, clay particle, basically clay. And clay is a highly charged, lots of negative charges, so very hydrophobic. So asphaltene and things like that stick to it. And you don't want to use this for upgrading because you have too much clay in it, and that is something like a few percentage of the material is clay. So you have to remove them somehow, to below 300 parts per million, and that's what the refineries want. And so that's one of my objective, how to get rid of this particle. So we have some ideas, and that's where it's all coming along. So another idea is that is it possible to heat the oil sands, because oil sands are basically very viscous material, and if you can reduce the viscosity, then you can pump it out practically. So right now what they are using, two pipelines, it goes down and then go parallel, 5 meters separated, and they send steam for months and months until you heat the whole ground around it, and then the oil, the bitumen start to get viscosity start decreasing and start draining, and you can pump it out and then take it out. So this is called steam assisted gravity drain. So we are thinking that maybe it's possible to heat it using this idea of Tesla that I talked about. So I have a student, she came from IIT Roorkee, so she is doing experiment now. This is some of the results that we have. We can actually heat the whole sand using this idea and reach something like 80 degree within couple of hours. And if you can also use steam together if you want. So we want to use this idea to heat it, and so we can reduce the viscosity. And currently people are using like IR heating, just to apply voltage and current and then heat the whole thing up, and that is very inefficient. What we are doing is that is a reactive power. Remember, there is a slight difference here. So this is very, very inefficient technique. Well, our idea looks like a more better actually. Maybe we are thinking of using together with the SAGD, so we don't have to come up with drill another hole, existing hole, or things that are already depleted, because the maximum efficiency right now is 50%. So 50% material is still around. So we can use that to get more out. So another approach, maybe in the ocean, wind energy, you have lots of wind in the ocean around in Arabian Sea or Bay of Bengal. You can actually bring this to the shore without having wires or cables running from one point to another point. So here is a little trick that you can think of. The resistance R is rho L divided by A, right, from freshman physics. But if the distance increases, area scales, of course, area will be L square. Actually, so the resistance actually decreases. Resistance from here to Canada is actually 0.03 ohms compared to from here to there, it will be maybe few thousand, ohms. And here, if you increase the area, resistance will go down practically. So the longer distance, resistance is very small. I didn't realize this thing until maybe a couple of years ago. But dang, this is a easy thing to remember. Of course, there are lots of problems. How do you make a contact to the ground? Ground is the insulator, and you have to have very good contact. So this is where we are thinking about as fractal ideas, and trees, of course, the roots look like it has a huge surface area. So there are many different ways you can increase this area of contact and reduce the contact resistance. So another idea is that you can power electrical vehicles actually. That's a big push actually in the US. President Obama wants to go from Chicago to Washington DC without stopping to charge his battery. So right now the batteries, even the Tesla cars, it doesn't go that far, maybe 200 kilometers or something maximum. So this is an idea. So again, using so here we have the one wire coming. Of course, we split it into two because this sometimes there are breaks in this rail. So it's a toy train from Charles's son or something. And then we have the little receiver here. That's where it's going to take the power coming through the track. And then of course there is some electronics because it's a DC motor, and it works fine. So you can see that it is moving. So one possibility is that you can have highways with some metal type stripes, or you can have a conducting paint, and the car will be as long as car is very close, you can get the power out of this thing, or you can even touch the thing. So probably that is a good idea. Another one is that of course we calling this auto transformer is the same thing. Remember what I told you about the heating of the tailing. Tailing is a bad thing. There is lots of water left over from the bitumen extraction with lots of clay and sand and so on, and we want to dewater the lakes. So again, only thing you have to remember is that the dielectrophoretic forces acting on the particles is proportional to E square. So the higher the E, higher the force between them, and you can make them collide together or something like that. So they will come closer, and once they come closer, their radius increases, and the settling velocity, from the Stokes equation is V is equal to proportional to A square, radius square, right? So as long as they can come close together, they will start settling. So that's what we have done. So you have to understand what happens at the nanoscale. Here is the electrostatic forces which are repulsive. I said this clay particles have lots of negative charge on it, so they can stay apart. Of course, they have the van der Waals interaction, which is attractive coupling. So they basically stay in their equilibrium location. And so what we are trying to do is that somehow overcome this repulsive forces by making them collide, and so they increase their size so they can settle faster. So I have this student from again IIT Roorkee. He was a silver medalist there. So he joined us, and I told him, okay, why don't we try this electric field idea? Maybe it will work. So we tried it. So this is the way it looks like. Muddy, is taken out of this tailing pond. It's like from Google map it looks like a beautiful lake, but this is the color of this thing. So and then we applied electric field onto it, and then you can see that of course within few minutes the bitumen separated on the top, and the tailing actually separated. You can see that all the sand and clay particle went down, and we got a clean liquid particle. Of course, there are some more particle in it. We have to make the system better. So you can within maybe in an hour or so, you can see all the sand and the bigger particles settled right away. And you get a much more cleaner water, and that's what we have been looking for. And this is the control sample, and this is the tailing. So all the particles gone practically. So it's working. So so we are thinking of maybe we can have this Tesla transformer sit on a boat, and boat will be remotely controlled, and it will run around the lake for 24 hours a day, 7 days a week, all year round, provided it doesn't freeze, and it will settle all the particles eventually. And you can get the clean water and then maybe process it later. So we have done this thing, and another thing they wanted was that let's see, the whatever is left behind. I told you that the tailing at the end, it's like a yogurt, and the Canadian law right now states that all the companies should get rid of it. So the companies are saying that do whatever you want, get rid of it. We don't care, and come up with some idea. So this is Arnish after treatment, after a couple of, 1 day or something, it will become a solid piece basically. And you can walk on it. So that's what they want. They want to make this solid, so and the legs will be gone. So another idea is that there are lots of pipelines. The Enbridge is a big company, and this is where it's all produced. And see, it's all sent to actually Houston for upgrading. So there are thousands of miles of pipeline. And anytime a pipeline has a leak or something, and it leaks out, say, 1 gallon of oil or something, it will cost thousands of dollars to clean up that part. It's like 1 to 1,000 ratio. And so any leak, if you can detect early, it is a very good idea. And of course, you can have lots of sensors looking for hydrocarbon, pressure, and all those things. But how do we power them? You have thousands of miles, so if somebody keeps changing the battery, that will be continuously changing forever, right? So that wouldn't work. So we have to look at some other application like the one we are talking about. So there are lots of accidents happen all the time, fire. So we need this thing. So applications are power remote. Another application will be powering remote communities. Just like in India, Canada also has lots of villages of 5 people or 100 people. Up in the north is all completely covered with snow. It's very hard to get a infrastructure there, just like in India. So India and Canada has lots of things in common, and electricity for natural disasters, like Hurricane Katrina came to Louisiana, New Orleans, and suddenly they lost power for weeks. When I was in Tennessee, we had a superstorm or some snowstorm came around. Power was lost for 3 weeks, because it's very hard to get to places because when it is too cold and lots of snow. And of course, we talked about implantable sensors and then distributed network sensors for pipeline, border security, environmental monitoring, and so on. And it also has applications in military. We always think in terms of military because we used to be at Oak Ridge, and the generals used to come and see us all the time with problems. And one of them, and I still remember, is that they looking at the landmines. Landmines. I'm sure India-Pakistan border and so on has lots of UXOs and landmines, and we can use this idea actually create the power and triangulate them, so you can actually get rid of it, basically burn up all the electronics or whatever involved in it. And if you see the US soldier, they carry this big backpack. I'm sure it is same in Indian Army too, and most of these are batteries because they have night vision cameras and all the sensors and devices. So instead they can carry a lighter bag with more bullets, weapons, rather than carrying batteries. Suppose you want to get a camp, and of course you have to have a power line and things like that. And you may not need it. You can have the idea that we talked about. And there are lots of other applications like intruder sensors and environmental sensors, unmanned electric vehicles. So that's one area that's getting very popular right now. Is that you don't need not only electric vehicles, unmanned vehicles. That means I was in some place in the huge tower with say 18 elevators. So there is no button for any elevators. So you go there and then there is a monitor like this one. You say I want to go to 56th floor, you enter the 56th, and it will give you a number of the elevator. You go there and it will take you there. So it is the computer is managing it much better than people entering their own. So same way, what is going to happen in the future is that if you want to go someplace, you enter this into the website, and the car will come, an unmanned car will come. You get into there, and your neighbors or who are going in that direction, they can all go, because it's all automatic basically. So for that you need power and you need intelligence. So that type of work is going on in many universities around. So like I said, India has around 600,000 villages, and how do we power them, right? If you can power them, if you can get electricity to the villages, then you will have these villages 600,000 economic engines, right? The reason it's not working out is that because the power is the most important thing, and how do we deliver this power? Of course, there are wind and solar, and they may not match with the villages. Wherever there are more wind is someplace and the village is someplace else. We can use this type of ideas. Anyway, this is the ongoing research, making a more efficient electrical contact to the earth. This is the most important thing, and this is where Tesla had lots of trouble. I think we know how to go around it, and making theft proof. This is where Tesla went wrong, and he didn't have all the electronics, and now you have wonderful electronics, and we can actually make it coded power. So wherever Tesla had trouble, after 100 years, we know how to do it, improving the efficiency, and of course investigating the environmental and health effect and increasing power. I don't want to continue anymore, and I will stop it here, and I will be happy to take your questions. Remember that this is a first time I give this talk. Of course it's kind of a little rough because you are the first people to see these things, and this is never shown to anybody else. I thought I will start at home before I show it to somebody else, right? Thanks. So I am ready to go ahead.
How does the efficiency compare with traditional wired transmission, long distance power transmission?
Oh, with the two wires is pretty efficient stuff. Of course, except for IR loss, there is nothing. So we will have much more loss because if you use earth, because the resistance is much higher. And which one? That's if you can get a very high Q. That if you can get a very high Q, you can store the power. So the trick is how do you make the Q much higher?
In all of this, the frequencies concerned are all very high?
The frequency we made the frequency around say 6 megahertz, because that's what we have in the lab. You can use anything you want practically. Of course, we have to think about the health effects too, because some people are worried about if you go high frequency, maybe there may be some health effects. But people use cell phone all the time, which is at megahertz, right? So we have to look into that part and see which one is more safe.
You come across the 0-point energy devices?
0-point quantum mechanics, yeah, that's what I said. There is a Tesla cult going around. Of course, Tesla is a polarizing figure because lots of people who are not really scientists, they believe that Tesla knew everything. He's all kinds of different things. I don't know very much about it. I know talked about the 0-point energy from quantum mechanics, but we don't know how to tap it at this moment in time.
Apparently, that also involves very high frequency.
Probably I am not an expert in that area. I know, I have read about it, looked at it, but I don't have that intuitive feeling yet. Maybe I think about it a little bit more. Maybe at this time I don't have an intuitive feeling about it.
See, when you have two wires in a well-defined circuit, we are in full control of it. But if you just use earth as one of the electrode and all that, interference between my system and your system.
That's a good question. You have a uncontrolled resistance between your source and your whatever it is picking up, because the ground as another component. But remember, it's a resonant devices. So I will take you back to Huygens, our wave theory guy. When Huygens was sick with the fever and he was lying down in Denmark, and he is a clockmaker, so he makes the get the pendulum going on one clock, and then the other one, and then he lied down. And what happens is that he kind of figured it out that somehow they communicate. This is called Huygens pendulum, right? And even though these vibrations actually go through the wall, and all of them become either one phase or opposite phase, right? So similarly, because it's a resonant coupling, even if a very little interaction, that coupling can be amplified. And this happened to me when I was in Tennessee. I'm lying down with my little daughter when she was only a few months old, looking at the ceiling, and there is a fan and there is a little wire, string that you can pull to. And at the end there is a bead and another little string sticking out, and that string was going like crazy. I mean, I said, what is happening? It's vibrating like crazy. So I went around the whole house looking around, and then I found out that it's a 3-story house or something. There is a place, washing machine was working, and you cannot even hear it, but it's coupling through the wooden frame of the house, and this guy is going like nuts because it's exactly coupling. So resonance is a amazing thing, and everything is a resonance actually, optics. So if you can use the resonance, and that's what we are trying to use here, and you will have less loss and amplify almost everything practically. Yeah, see, there are lots of things that we don't know about at this time. I know there are lots of things. I don't know those things, but I heard about it. Anyway.
Sir, you spoke about that single wired power. Virtually, if we see, it's about completing path through capacitance. So in our case, the distance is really high. That is offering a high amount of reactance. So what would be the stand over the higher power rating? Let's say I want to run 1 kilowatt motor. Let's say I want to run a few hundreds of watt of motor. That reactance offered is really high, as the distance is very large in our case. So what would be the...
Let me rephrase your question if I understand correctly. You are asking, if I go higher power, what will happen? Is that right? So actually I don't know the answer because we haven't done the experiment. Only I can speculate it at this moment in time. But according to physics, it should scale. That's what it says. If it scales, then we will have a device that can power higher power. But I don't know at this moment in time. Only thing we have done is a low power, 50 watts or 100 watts. Even the 100-meter distance we have done is like a few watts at this moment in time. And mostly because we were worried about what is the public perception of this thing. You don't want to have, always remember that we are at their mercy. We have to give them the right information. Otherwise they will say that, oh, you're doing crazy things or whatever, That's what happened to Tesla. Say, remember the story I was telling, lots of people don't like physicists and all those people because of the perception in the US from the TV shows and things like that. All scientists are bad guys. They are trying to blow up the world like a Batman, and then somebody has to come and save the world, right, from this bad guy. And all the bad guys are modeled after Tesla. And that's what Edison's best, whatever he did, marketing was make Tesla look like a really crazy guy going to kill everybody in the planet. And it worked. And there are lots of novels and books and TV shows and where scientists and engineers are the crazy guys ready to kill everybody, and then some bad man was to come and save this world.
I read something interesting over there that people were trying to find out how all these guys like Tesla and Edison and all these people came up with incredible ideas. G and all that. How would you figure out a helicopter? I mean, there was no aircraft even at that time. And to even draw it out was incredible. It's like saying that the Indian gods flew in the sky. How did they fly? Who wrote it? When there was no aircraft, how could they write about aircraft? They described nuclear explosions when there was no nuclear device at that time. So what's the truth behind all this kind of stuff? So they used to interview these people to find out how they figured out all these things, like, what did you do to get these ideas? Apparently, the common factor amongst all of them is that they said that they used to go into a meditative state. And then they used to think about the things that they were interested in. And sometimes ideas would come to them which were not even connected with what they were doing. And they would immediately sit down and write it all down. Like the description of the helicopter and all that. He sees it as a picture. And he draws it out. When he does it, he doesn't even know what it means.
Actually, that's what Tesla described to the induction motor. He went into a trance and everything became clear to him, and he wrote it down after that trance. So,
Are you able to figure out what it's all about?
I don't know. See, I am nothing compared to these guys.
My take on this. You must be aware that the West is now very deeply involved in research on lifespan, afterlife, and all those kind of things. And they are doing more work on it than anybody in the East is doing. Actually, what they are doing is validating what the people in the East believe in. Present day people in the East don't believe in it, but this is what's come from the ages, and the Westerners now say it's correct. So what they're saying is that in the next dimension, all the information is available, everything. So when you're able to have a conduit between your existence and that one, you get the information, which is what all these great people did.
I mean, I cannot agree more. Even I was reading what you call Ramanujam as a biography. He says the same thing, right? No, not autobiography. He said he got vision from Kali or something like that.
So basically, it also comes down to the other simple thing, like they took slices of all of these brain of all these very clever guys to find out what's different about their brain compared to an average citizen, and they sent those slices all over the globe so that everybody could, scientists could investigate and find out the difference. And the final conclusion that they came to was there was no difference. So what was the difference? The difference was they were able to channelize their energy between between the point which is giving the information and themselves. So which basically means IQ, as we understand, is all rubbish. It's actually the ability to make the connection which is what we are measuring.
Yeah, ability to make connection is the most important thing. That's what I tell my students to stop working, start thinking. Probably, I don't know what I have done experiments only with the tailings and the oil sands. So we have to run some experiment for a specific.
What size of?
We're going to scale it up. Actually, these are huge ponds, right? So there are different ideas we thought about, like a mesh, and we have the little boat, and all kinds of different ideas. But the most important thing is demonstrating it at a small scale and finding out what are the parameters that controls these things, and whether they are scalable. So we believe that it's scalable at this moment in time.
How efficient is it compared to other?
See, right now they are take the sludge and put it on pump it down to a small area or big area with a small thickness, maybe like a couple of 1 feet or something like 1 foot, and then pray every day, and the sun will come and then dry it out, and then bring a bulldozer and push it out. So they can do it only every 14 days at this moment in time. So knowing northern Alberta is so you can June, July, August, and then after that it's all cold. So 3 months. So 3 months, every 15 days. So you can do it only 6 times a year. So at that rate, if you remove the tailings, it will take hundreds and hundreds of years. So they want to accelerate it.
So where does the American military stand with regard to energy devices?
See, I left Oak Ridge. I don't know. This is I'm in a different country now. So suddenly I realized that, oh, there is a barrier. I have no idea. When I was at Oak Ridge, I knew lots of things. Now once you leave the country, it's like a very different story. So my information knowledge is 5 years old. Okay, thanks.